Hi, everybody. Welcome to today's Spectral Geometry in the Clouds seminar. Today we have Mikhail Cherdantsev with us, who will speak to us about stochastic high contrast homogenization. So Misha, the floor is yours.
Thank you, Jean, and thank you to Alexander for inviting to give a talk at this seminar across 2 continents, right? At least. I will speak today about stochastic high contrast homogenization. This is a very new area. There is not much work done at all. Homogenization is very popular and has been developing for a number of decades. And actually the first questions about homogenization were asked by such people like Maxwell and Einstein, for example, when they considered heterogeneous media. And the question is, what is the effective behavior of such media? Well, mathematically rigorous theories started appearing somewhere in 60s, right? 70s and so on. And there was a lot of development in periodic homogenization, in stochastic homogenization of random media. More recently, there was new directions in high contrast periodic homogenization, but until recently, high contrast and stochastic or random setting haven't been considered together at the same time. So essentially, we are offering a framework for working in this setting. Okay, this was a short introduction. Here is the plan of the talk. So I will talk quickly about periodic high contrast homogenization, because lots of effects that we see in random stochastic high contrast case are very similar to the periodic high contrast case, especially this band gap spectrum of the operators, band gap structure of the spectrum. And then I will move on to our stochastic high contrast setting. I will talk about the homogenized operator A-home, its spectrum, about spectral convergence in bounded domains, properties of Zhikov's beta function, the function that describes the spectrum of the homogenized operator. And then I will move on to the whole space setting, where things become more intriguing. In particular, there is no spectral convergence in contrast to periodic high contrast case. And I will talk about the limit of the spectra and how to describe this limit. And at the end, I will talk about localized eigenvalues on the defect. Okay, so periodic high contrast setting was, I guess, first mathematically rigorously studied by Zhikov in his 2 papers from 2000 and 2004. The setting is very straightforward. You have some medium with inclusions. The inclusions are periodically arranged. The characteristic size of each inclusion and the distance between them for the epsilon, all inclusions are identical. And you consider this divergence type operator. And you assume that the coefficients of this operator are of order 1 in the base medium, or stiff component. Sometimes we also call it stiff component by analogy to elasticity. And on inclusions, you assume that the coefficients are for the epsilon squared. To make things simple, we just assume this is epsilon squared times the identity matrix. This scaling between the size of the microstructure and epsilon, and this magnitude of the coefficient on the soft component is important. This is where you see these band gap effects of the spectrum. Okay, but first you start from a resolvent type problem for this operator. and you want to understand what happens when you pass to the limit as the size of the microstructure goes to 0. Simultaneously, you have that this soft the coefficient on the soft inclusions degenerates. You can see that you can show then that the limit problem is described by the specific two-scale operator. So it acts on functions of two variables, where x is the macroscopic variable and y is the microscopic variable that lives on this periodic cell. This periodic cell, which I denote by Q. Okay, and the interesting thing about this is that you can actually, so two-scale problem, you can represent the solution of as a sum of two functions. Oops. So the first function doesn't depend on the microscopic variable y, but the second function does depend on this variable. It is 0 outside the inclusion, the reference inclusion Q0. And inside it solves some resultant problem. And then if you if you're interested in the spectrum of such two-scale operator, well, you formally write this spectral problem, and you can see that you can separate variables in the second equation, and so this function v that has the information about the microscopic behavior of this two-scale operator can be represented as this product of u0, the macroscopic function, and some function b, which solves this Dirichlet resultant problem on the reference inclusion Q0. If you plug this representation back into the first equation, so let me go back to this problem. So these angle brackets Q means that you just integrate the function with respect to variable y on the periodic cell Q. So you see that you can represent the macroscopic spectral equation in this form. So now you get rid of the microscopic function altogether. V disappears. It just feeds into this spectral parameter function beta, which we call G plus beta function, and which can be represented by this formula here. From this formula, the first equation, it's not clear how this function beta looks like, but if you write the spectral decomposition of the solution B, of the function B, the solution to this resultant problem on the reference inclusion Q0, you can see that you can represent beta function, G plus beta function, as this infinite series where nu j's and phi j's are eigenvalues and eigenfunctions of the Laplacian, Dirichlet Laplacian on this inclusion. And you can see that this function blows up as lambda approaches these eigenvalues. The spectrum of the homogenized operator can be described as all points where beta of lambda is non-negative, all points of the spectrum of the Dirichlet Laplacian, which is discrete. Here is the picture. So what you can see here, those red dots are eigenvalues of the Dirichlet Laplacian. The red dots that are, so red bands are the bands of the spectrum where beta, G plus beta function is non-negative. So this is the whole space setting, right? If you consider the homogenized operator in the whole space, then these red dots in the gaps, in the black gaps, where beta of lambda is negative, these are eigenvalues of the Dirichlet Laplacian on the inclusions which have zero mean eigenfunctions. So if you go back and we look at this formula, we see that we need to integrate the function the eigenfunction, right? And if it has zero mean, it just does not contribute to beta function, and there is no blow up at those eigenvalues. So you can, so though zero mean eigenvalues with zero mean eigenfunctions are still in the domain of function beta of lambda. So you can see this band gap structure of the spectrum. And you can prove convergence of the spectra. So the spectra of the this periodic operators A epsilon with this microscopic periodic structure and high contrast, they converge to the spectrum of the homogenized operator, the one that you see on the picture. If you consider a bounded domain setting, instead of bands, you will have a discrete spectrum populating these bands and accumulating to the right ends of the bands. If you look at this equation, this is where beta of lambda equals to the eigenvalue of, say, Dirichlet problem on this bounded domain. Any questions so far? Basically, this is all about high contrast periodic problems, and so this is the reason why high contrast case is interesting, is because you have this band gap spectrum in the limit, you have spectral convergence. So for small enough epsilon, you definitely have gaps in the spectrum of A epsilon, and there will be infinitely many of them. The difference from normal non-high contrast classical periodic operators is that for classical periodic operators, normally there would be finite number of gaps in the spectrum, whereas in this case, in the limit, you have infinitely many gaps. And beta of lambda is also very interesting and important function. It gives more information about decay of localized eigenfunctions. I will speak about it a bit later. So now the question is, what happens in high contrast random settings? So assume now you have a similar picture, but your inclusions are distributed randomly in the space. Okay, so everything else is the same. Again, we look at this resultant problem. Let epsilon go to 0 and try to find a limit operator. Okay, and it turns out that the limit operator can be described in a very similar terms compared to the high contrast periodic setting. So it has to scale structure. So it is defined on functions which can be decomposed as a function u naught of x, which depends only on the macroscopic variable, plus a function v, which depends on x and omega. Now, omega is a counterpart of y, but now this is an element of the probability space. But essentially, it plays exactly the same role. And you can, there are lots of tricks which are technically can be quite complicated when you can go back and forth between the actual physical space and the probability space. And there are some examples where you can easily explicitly see how these things work. So you can, in general, you start, in our assumptions, we start from a absolutely general probability space. Well, it needs to be separable, that's all. And you define these random coefficients in a very general form. But for the purpose of just trying to intuitively understand what's going on, you can think about a periodic lattice. So these blue lines here, they're just periodic lattice. And then you, this is an example, then you put an inclusion in each square of this lattice with probability 1/2. So the probability space that corresponds to this thing consists of those elements omega, which in fact consist of functions of variable y, which lives in a unit periodic square or cube, more general, and sequences which take values sequences where z belongs to zd, so a discrete lattice, and they take values in the set 0, 1. And then you say, okay, we put inclusion in an element of the lattice if the corresponding omega z, where z corresponds to the left bottom corner of this square, if this omega z equals to 1, we put an inclusion, and if omega z equals to 0, there is no inclusion. This is a very simple, explicit example of such a probability space, and then you say, and then using this space, you can generate inclusions in the. This will be exactly what we see here. So you generate the inclusions on the physical space. Okay, this is some intuitive picture. Let us go back to. Well, the reason why I showed you is to explain that how you can easily see that there is an interaction between an abstract probability space and the actual physical space. So in this example, y represents this actual physical space, variable y. Okay, so essentially these in that specific examples can be treated as functions v depending on x and variable y, and also this this extra parameter. Well, let us call it tilde because we have used omega already here. So this is omega, and this second variable is tilde, omega tilde. Okay. So now you can see that this is a very similar to the two-scale periodic case setting, and in a very similar way you can decompose. You can look at the spectral problem, look at the second equation. Again, this second equation is on the probabilities. You can lives on the probability space. So this operator acts on the probability space, probabilistic Laplacian, right? But you can have there is a way to see it as an operator acting on physical space. And then you separate the variables. You can represent v as lambda u naught times a function b, which solves this resolvent problem. So again, this is an abstract resolvent problem in this abstract probability space, but it can be seen as a Dirichlet Laplacian on inclusions. So you plug this back and you see that into the first equation, and you have this spectral problem for the macroscopic operator with this spectral parameter beta of lambda, Zhikov's beta function, but now it's a stochastic stochastic variant of this function, right? It has exactly the same definition, in fact, modulo that this function b lives in the probability space. And the spectrum of the operator has exactly the same structure as in the probability setting, sorry, as in the periodic setting. So it is all points where beta of lambda is non-negative, plus all points of the spectrum of this Dirichlet Laplacian on the probability space, on the inclusion in the probability space. Okay. So we have some results on more specific results about the spectra of this operator home, namely about the spectrum of the probabilistic Laplacian, and how it relates to the spectrum of Dirichlet Laplacian on individual inclusions and the properties of Zhikov's beta function. So the first theorem tells us the following. So if you let me first explain the notation. So this O omega k is the following thing. So calligraphic O, let me use now my pen. Calligraphic O is a reference inclusion. Reference inclusion in the probability space. So O is a subset of omega, and it has physical counterparts. So if you fix, so if you throw dice once, it gives you well, if you throw dice, it gives you a specific distribution, random distribution of inclusions in the whole space. So throwing these dice tells you that for omega has this representation in physical space. You throw dice another time, you have a completely different distribution of random inclusions, right? So so omega here is that fixed dice throw, and you fix one specific random distribution of inclusions, which springs from this reference inclusion O. And O omega k is each individual inclusion in this configuration. So k runs from 0 to infinity, right? It's we just count them. Now you have probabilistic Laplacian. Sorry, now you have directly Laplacian on each individual inclusion. Now we live in the physical space. Now, if you consider spectra of all possible, of all these directly Laplacians on all of these inclusions, take the union and take the closure, you get the spectrum of probabilistic Laplacian for almost every realization. So for almost every realization of O in the physical space. In the case if you have just one shape, for example, a ball, the inclusion of one shape, same size, and the only randomness is in the distribution, in the spatial distribution of these identical inclusions, then there is nothing to discuss. The spectrum is exactly the spectrum of one inclusion. If you have two inclusions, two different shapes, you have two different two spectra of two operators, you combine them. This is the spectrum of probabilistic Laplacian. But if you have an infinite number of shapes, for example, a continuum, so the size of the inclusion is a ball, but it randomly picks the size from 1 to 2, for example, the radius. You will have a continuous bands of the spectrum of probabilistic Laplacian because you need to combine all possible spectra for these randomly sized inclusions. Okay, another theorem, you can prove properties, show that the Zhikov's function. So if let's quickly go back to the periodic case. So in the periodic case, you have everything explicit. And the properties of beta function are straightforward, right? Just from analyzing this thing, and this picture is straightforward. So in the general stochastic, in the specific setting which I've showed you here with this periodic, because everything is explicit, you can also show that Zhikov's beta function is in fact very similar to, and I'll show you an example soon, very similar to the periodic case. However, in the general case, there is no way that you can write things explicitly. This is the best you can do, this formula here. Let's try to. This formula here is the best you can do. It's not explicit. So you need to make some effort to study this Zhikov's beta function. But we can prove that, but because you can go between abstract probability space and physical space and study these objects on individual inclusions, you can actually prove that beta function is an increasing function. Moreover, its derivative is strictly positive. So here is the size of the reference inclusion in the probability space, which is always less than 1. Okay, so this is what I was explaining. So you can go between physical and probability space. So this is how it looks on the physical space. So this Tx omega for fixed omega is a function of x, and it takes a function that is defined in the probability space b of omega to be a function defined on the physical space on individual inclusions and 0 outside. So actually, the way to prove to study Zhikov beta function is exactly that thing. You need to take abstract beta function, on abstract probability space, and move everything to the physical space. So using some ergodic theory, the Birkhoff ergodic theorem, you can show that actually Zhikov's beta function can be represented as the limit of this expression. So what you do, you take a large ball, take all inclusions that are in this ball, take individual b functions on each inclusion, and take the average. And then you need to let the size of the ball go to infinity. And this is how you get beta of lambda. So in periodic case, this formula also holds, but it is trivial. In stochastic case, you need to make some effort to prove this. Examples. So if you go back to this example where you have identical inclusions distributed with probability one half inside the periodic lattice, you can write things explicitly, as I mentioned already. So this first part of the formula for Zhikov's beta function is exactly as in the periodic case. However, you need to multiply this second term by the average number of inclusions per unit volume. For example, if the probability of appearing an inclusion in a cell of periodic lattice is 1/2, this is going to be 1/2. If the probability is 1/3, this is going to be 1/3. But the actual picture of beta function is very similar. So it will slightly move compared to the periodic case, but everything else is the same. So the properties, the general properties are the same. A more advanced example, if you allow, and in fact, this is not only this formula works not only for the this example where you have periodic lattice. You can drop same identical inclusions randomly. Well, there are some assumptions. I didn't discuss these assumptions. Probably I will do it later. So the main assumption is that they are not supposed to touch each other. They need to be separated by a distance to allow these inclusions, to allow controllable extension inside each inclusion. These are standard techniques that we use, and I don't think, and these are unavoidable things. So these inclusions are not allowed to touch each other, but if you just drop them completely randomly, observing this restriction, this formula is also valid. And you need to just look at the number, multiply by an average number of inclusions per unit volume. Okay, a more advanced example, you take, for example, balls or any other shape and scale it by a parameter r. So this scaling parameter takes values in some bounded interval. And then if you, because of scaling, you can take, for example, all eigenvalues for the Dirichlet Laplacian on this inclusion on this shape. For R1, apply the scaling, and then it becomes not just a discrete set of eigenvalues, but a set of intervals, the ones that you can see here, right? So you kind of smudge them, but the rest is more or less similar. Well, if you assume identical distribution of sizes, the formula would be simpler. but if the distribution of sizes is not identical, is not trivial, so you may have less inclusions of one shape and more inclusions of one size and more inclusions of another, then you would have to integrate with the probability with respect to the probability measure of this distribution of sizes of scaling parameter, right? And from here comes the first interesting effect that this function Zhikov's beta function doesn't have to necessarily to blow up at the edges of the spectrum of the probabilistic Laplacian, of the spectrum of these inclusions, right? So if, for example, if we look at the right end of this band, where it meets the left end of the band of the spectrum on inclusions, which corresponds to probably R2, value R2. So when you approach value R2, if you don't have, if you assume that a probability measure, the density of the probability measure is very, very small, like goes to 0 around this value of the parameter, then you can more or less explicitly set this beta function to go to a finite value rather than to infinity. And a similar considerations on at the other end of the gap. Okay. Spectral convergence. One can prove a strong stochastic to scale resolvent convergence. So what is strong resolvent convergence? If you consider a resolvent problem and you write for a family of operators, and the right-hand sides converge strongly in some topology, then you get strong convergence of the solutions in the same topology. This is a strong resolvent convergence. It's a weaker than the resolvent estimates thing, but still, and normally it's much easier to prove. So the proof is quite standard and it works for exactly the same as in the periodic high contrast setting, but now this strong resolvent convergence is strong stochastic to scale resolvent convergence because we assume stochastic to scale convergence of the right hand sides and then get strong stochastic to scale convergence of the solutions. Okay, so once you have this resolvent convergence, which as I said is straightforward in this setting, it implies that the spectrum of the homogenized operator, the limit operator, is contained in this limit of the spectra of A epsilon. And this is very easy to see. If lambda is in the resolvent set for small enough epsilon, well, it's going to be in the, because of this strong resolvent convergence, it's going to be in the resolvent set for A hom, and the job is done. The opposite statement, opposite inclusion, is not trivial or not always possible. Well, in bounded domains, in bounded domain setting, if you consider you operate in a bounded domain with, say, directly boundary conditions, there is compactness. So if you take an eigenvalue of the operator A epsilon, which converges to some point, finite point, lambda naught, then you have compactness of corresponding eigenfunctions. So you pass to the limit, you use strong to scale resolvent convergence, which works in the same way for the spectral problems actually, and you get an eigenfunction of the limit operator in the end. So the lambda naught is going to be an eigenfunction of A hom. So you have Hausdorff convergence of the spectrum in the case of bounded domain. In the periodic setting, well, bounded domain is obvious, right? In whole space setting and periodic, in whole space problem periodic setting, one uses the fact that because the operator is periodic, all eigenfunctions are actually oscillating the L infinity, and you also have compactness in this way. Or you can use Bloch theory. And then you have also convergence of the spectrum in the sense of Hausdorff. However, in stochastic, whole space setting, there is no compactness. You cannot use this trick of that eigenfunctions are L infinity. They're actually not L infinity in general, and in general you don't have the Hausdorff convergence. So this limit of the spectra of A epsilon is in general strictly larger than the spectrum of A hom, the homogenized operator. Look again at so let us talk now about the limit of the spectra of A epsilon. To describe the limit, we need to introduce an analog of Zhikov's beta function. So we still haven't decided whether it is local or global, because it's local in one sense and is global in another sense. So I'll pull alongside the Zhikov's beta function, its formula. So this is not the definition, but the formula that you get from going to the physical space. So if you recall, there was this in the formula that I gave previously, you had a ball BR of radius R, but in fact you can define this and quantity on any bounded domain of reasonably regular, right? And it works exactly the same. It doesn't matter whether you take a cube. So here, this is a cube of size m centered at the origin, right? So the difference between beta and beta infinity is that for beta infinity, we calculate these averages over all possible cubes with all possible centers x. Take the supremum of this quantity over all x, and then pass to the limit, enlarging the size of the cube. So from this definition, first thing that you can see, it's straightforward that beta is less than beta infinity. So what we can so let me talk about physical interpretation of that things. It will give you an intuition of what's happening. So if we think about elastic problem analogy, so we're in a scalar case, but analogy works very well for elastic elasticity setting. So if the elasticity coefficients of this material are for the epsilon in the inclusion. It means that the material is very soft, but it has the same mass, right? The same density. So when you send a wave inside in this composite material, so it goes through this bulk medium, and these soft inclusions, they may react in different ways depending on the frequency of the wave. They may happen to be in counterphase. So when the base medium moves that way, your soft inclusions moves in the opposite, and then it acts as a anti-resonate. And there are lots of anti-resonators. It's a constant, more or less constant average. On average, it's a constant average density, right? And so it will stop wave from propagating because you're in the anti-resonance. If you choose pick a different frequency, you may be in the situation when the displacements of these soft inclusions coincide in the direction with the bulk displacement of the wave motion. And then you're in the resonant regime, and then it just amplifies the wave, right? As it this is the reason for this beta of lambda picture. So if you quickly go back to this picture, so the red bands where beta is positive, where this is where this resonant effect is very strong, right? And the wave is propagating and is amplified. If you're in the gap, this is where you have this thing is negative actually. So you're in the second term, you're in anti-resonant regime, and the wave is stopped from propagating. Okay, so now let us go back to this. So beta of lambda is this average resonance effect for the whole space. However, if you look at beta infinity, what happens is that I need to pull up another picture that I prepared. So think about this random distribution of inclusions. Normal, this is the average that is, if you just keep magnifying and looking at the bigger and bigger picture. So for example, you have average number of 1/3 inclusions per unit volume, right? Now, but because of the law of large numbers, there will be some areas of the space where you have much less inclusions, and there will so sparse distribution of inclusions, and the areas where you have much denser distribution of inclusions. For example, for sparse it could be 1/4 or could be empty completely of inclusions. In dense it could be 1/2 the average number of inclusions per unit volume. So, and these resonant effects will be different from, hence the resonant effects in these specific non-typical areas. So the areas where they have this average density of the inclusions is different from the average for the whole space, and we refer to them as non-typical areas. These resonance and anti-resonance effects will be influenced by this density. So for example, if we, let me go back to my favorite picture. So think about this. This is the resonant effect of an individual inclusion. So this second term here, right? And now if you don't have these inclusions at all in some non-typical area of space, there is no anti-resonant effects at all. So if this term was negative for an individual inclusion, but there are no such inclusions in this area of space, you just have lambda, positive spectral parameter. Spectral parameter locally it becomes positive, and there is no anti-resonance. If on the other hand, you have more inclusions than on average in that specific portion of space, the anti-resonant effects strengthens, and you go much further down along this vertical. So this local spectral parameter becomes very, much smaller, negative. And the same thing, same considerations work if you do the resonant effect. So when this is positive, again, if you have small number of inclusions locally, the resonant effect is not that strong. If you have lots of inclusions locally, the local density of inclusions is high, you have stronger resonant effect. Okay, this is the intuitive picture, and what you see here, that second term in this definition of beta infinity for fixed cube, this is, you can treat this as local resonant effect, and the whole thing you can think of as local spectral parameter. This is where the idea of the limit spectrum comes. So we define the set G such that it contains all lambdas for which beta infinity is non-negative, plus the spectrum of the probabilistic Laplacian. And if you compare it to this definition, to the description of the spectrum of the homogenized operator, the structure is exactly the same. The difference is that you have beta infinity here, beta infinity function, and just beta function here. Okay, so the general result is the following. The spectrum of A home is contained in the limits of the spectra of A epsilon, which in turn is contained in the set G. And if we make an additional assumption that the correlation of the distribution of inclusions has finite range. So, for example, there exists a distance d such that and we fix a point, then what happens around this point has nothing to do with what happens outside the ball of radius d. So they don't feel each other at certain distance. Then you can prove actually that the limit of the spectra is exactly this set G, which is defined by beta infinity function. Let us move on. So what is this So what is this additional spectrum that you don't see in the periodic case, right? You already probably have the flavor of it. So it comes from bit infinity, and we talked about non-typical areas. This is where bit infinity, this precursor for bit infinity, this local spectral average is different from beta of lambda, right? Okay, so the idea is that we need to somehow study this or try to eliminate these non-typical areas to see to be able to characterize the difference between the set G, or the limit of the spectrum of A epsilon, and the spectrum of the limit operator A home. And this is the idea is to define. We define statistically relevant limiting spectrum of A epsilon as a set of points lambda for which one can find there exists family of functions for each natural L. There exists a family psi epsilon for such that for each epsilon it's from the domain of A epsilon, right? And then, well, this is the standard thing that you can see in Weil's, in the definition of a Weil sequence, right? This is we think about approximate eigenfunctions, right? So Weil sequence, if you think about a Weil sequence, it's a sequence of approximate eigenfunctions, so that in the limit it approximates, well, it has a smaller and smaller error like this. So this is exactly the same object, but now we make an extra assumptions about. So we make an extra assumptions about these objects. So first we require that for each L. So forget about this, to simplify things, so you can forget about this lim sup and lim inf. And let's just say that for each L, we fix a cube centered at the origin of size L. And we require that the norm, part of the norm, part of the energy of this approximate eigenfunction contained in this cube divided by the whole energy of this approximate eigenfunction is greater than some positive constant. So that the energy is substantial part of the energy is contained in a fixed cube of size L. And then if under this assumption we have this property that this error term goes to zero if you first pass to the limit as epsilon goes to zero, and then let L go to infinity. So when you pass along the first limit, you normally would get a non-zero value, which depends on L, and but it goes to zero, vanishes as L go, as you make these cubes larger and larger. So this the idea of this definition is that you stay low around some fixed wall. You don't go around the whole space, and when you let epsilon go to zero for this fixed cube, sorry, not wall, fixed cube, all these non-typical areas, they shrink faster than they approach to this cube, so the effect on the spectral behavior is negligent, and in the limit it disappears. That's the idea. So it uses these ergodic theorem ideas. So the statement is the following. So the statistically relevant limiting spectrum of A epsilon is exactly the spectrum of the homogenized operator. So you chuck away the effect of the non-typical areas by considering these approximate eigenfunctions or quasimodes. So one can go a step further. So if you look at the proof of the statement, in order to show that an eigenvalue is in the statistically relevant limiting, so some lambda is in this a lambda which is in the spectrum of a home also belongs to the statistically relevant limiting spectrum, you need to more or less explicitly construct these families of approximate eigenfunctions or quasimodes. And this construction instructs the next definition. So if you slightly change the definition and allow and actually assume the existence of these quasimodes on an elements of the spectrum of A epsilon, I don't want to bring this definition up because it's slightly more complicated, but and it involves some specific estimates. So you get a specific error terms for this when you make the construction of approximate eigenfunctions. Then you can define a subset of the spectrum of A epsilon and show that this subset, which we call approximate statistically relevant spectrum, that this subset converges to the spectrum of A home. Okay, so I still have a couple of minutes, right? Don't I?
Yes, absolutely.
Okay, so let us move on to the next topic, which I wanted to mention. So if you now consider this random high contrast environment, and introduce a defect. This is a fixed size defect, so it's fixed. The epsilon goes, but it stays there, S2, with order 1 coefficients inside. So this is then you can expect eigenfunctions localizing on this defect if you are inside of the gaps of this spectrum of the set G. So for high contrast, for high contrast periodic case, for high contrast periodic setting, it was considered by my supervisors, Ilya Kamotsky and Valery Smyshlaev, and then they did half of the problem, and then I did the second half of the problem. Incidentally, well, they published much later than I published my paper, but their paper was ready 3 years before mine was ready, so I don't know what's happened, why it took them so long to. Anyway, so in the periodic setting, and this is the idea behind these photonic crystal fibers. You can see the defect inside the periodic structure. This is where you have a localization. So first thing that you need to know is that when you introduce a defect, you don't change the essential spectrum, so the bands and gaps of your operator don't move, and then only discrete eigenvalues can appear there, and then you need to prove that these correspond to localized eigenfunctions, which you localize on the defect. So you can do, and you only consider those lambdas which lie in the gaps of the homogenized operator. Now here you need to look at the lambdas which lie in the gaps of this set G, which is larger than the spectrum of the homogenized operator. But once you choose these eigenvalues, you can prove that there are. So this is the rigorous statement, which and the analog is true for the periodic high contrast setting. So if lambda is an eigenvalue of this homogenized operator with the defect, then there exists a sequence of eigenvalues of the high contrast operator with the defect converging to this lambda naught, and vice versa. If you have a sequence of eigenvalues of A epsilon D and it converges to some finite number, then this number and the lambda and this number is in the gap of the set G, then this needs to be an eigenvalue of the A home D. And also you have convergence of eigenfunctions, and also you have exponential localization of the eigenfunctions to the defect. So let us look at the localization. In periodic case, the order of exponential decay is alpha, where alpha is the square root of the modulus of beta of lambda. So let me remind you, you are inside the gap, is inside one of the gaps, so beta of lambda is negative. If you move towards the left of the gap, beta of lambda goes to minus infinity, so absolute value becomes goes to plus infinity, you have square root of it. So if you move to the left of the gap, the localization effect strengthens. If you move to the right of the gap, beta goes to 0, so localization effect weakens. This is periodic setting. So for stochastic setting, localization effect is similar, but it is proportional to the square root of the beta infinity function, which describes the set G. So if you are in the gap of the set G, beta infinity is negative, you have localization, and with exactly the same effect. If you move to the left of the gap, the localization effect strengthens. If you move to the right, it weakens. However, we believe that this is not an optimal estimate of this localization exponent, and in fact there must be beta there rather than beta infinity, but we couldn't prove this. So maybe we will address this issue at some point later. So I still have 1 minute. I have a couple of more slides. I just wanted to flash for you the assumptions. So these are all our assumptions. They're absolutely simple. So you have so your inclusions are disconnected, open sets. They don't touch each other. So there are beta, b, k, omega. These are extension domains. So each inclusion can be surrounded by an extension domain, right, not touching the other inclusion. And the boundaries of the inclusions are uniformly regular, and the specific assumption is they're minimally smooth. So it's more or less equivalent to uniform Lipschitzness. You also have an assumption on the size of the inclusions, which is the same extension domains. That's all for most part of the paper. The last part of the one of the results, the Hausdorff convergence of the spectra, requires this finite range correlation assumption, the last one. So these are very elegant and simple assumptions, but we've started from something like this. If you look at this, we thought about parameterizing these inclusions, talking about measurability of this parameterization, etc. It was insanely complicated. However, we managed to get all these measurability properties out of these very simple assumptions. And the last slide, I need to mention just I only know about one piece of work in this area. So this is by Amazin, Pyatnitsky, and Zhizhina. They considered a parabolic problem with time, and then some of the results partially overlapped with our results, but if you disregard if you consider the stationary case, our setting is much more general, and we have completely different methods. Future work, we at the moment we are generalizing this scalar problem, scalar setting to the setting of systems for elasticity, starting with elasticity, and here is the field of work in periodic setting. And then we next we will be looking at partial degeneracy, where you don't have a full high contrast, but on the inclusions you have partial high contrast. This is again in the case of systems. Okay, and sorry for taking a bit more time than I was supposed to. So thank you very much for your attention. I hope it was interesting and entertaining, and it's question time.
Thank you very much.
If you have any time for questions.
Thank you, Misha, for the talk. We do indeed have time for questions. So please, if you have any question, just unmute yourself and go ahead. You can ask a question. So I'll start. I have a very simple question myself. At the beginning, you said that the weight of the inclusion was epsilon square, right? At the very beginning?
Yes.
Is it the case throughout the paper? And what's the role of the square? Is it?
This comes from this can be seen from very simple asymptotic ansatz. If you substitute functions which, so essentially what you have is, let me do some writing. So you have two-scale limit problem, right? So, and if you replace the first variable y with x over epsilon, so this takes care of this periodic microstructure, and you substitute it into the equation, you see that this is where you need epsilon squared, so that and the other cases where instead of epsilon squared you have epsilon to the power less than 2 or greater than 2, you have in the limit some degenerate cases, degenerate in the sense that you don't get this two-scale problem. I don't remember from the top of my head, I don't remember what it is now, but it's something very trivial. And
so the spectrum will diverge or something like that?
Sorry?
The spectrum would collapse or then something like that.
So you won't get a two-scale operator, I guess, in the first place. At least with when the coefficients are less than epsilon, much smaller than epsilon squared, much larger, right? Well, yeah, I can't comment on this because it was a long time ago when I looked at this, and I don't remember the particulars. But it's another way to see it is that if you think about big formulation, you have epsilon squared on the soft components, so s naught epsilon. You have multiplied by a test function, integrate by parts, you get something like this, plus on the stiff component, you have order 1 things. And then if you write energy estimates, you see that this is, so you replace the test function with the unknown function u, right, or the solution of your problem u, and this needs to be bounded. So you see that on the soft inclusions, which are of the size epsilon, right, you have the gradient of u is of order 1 over epsilon, and this exactly corresponds to this ansatz. And when you have something different from epsilon squared here, you have completely different ansatz.
Okay, thank you. Does anyone else wants to comment or ask a question to Misha?
I'd have a question. I mean, I guess it's maybe a bit more philosophical in what. So for one, I understand that you're doing there is that you have this high contrast homogenization, and you're trying to find this function, the appropriate limit using this function, this Zhikov beta function. Would it be possible or an interesting problem to decide on this limit function at the end and find some homogenization process with either some parameters that would converge to that to that specific limit? Or is there some sort of theory of universality classes?
Well, if you just look at what's happening, so how you get this beta of lambda and how you can calculate it, essentially beta is determined by the spectrum of the inclusions, of individual inclusions. So if you can play with the spectrum of individual inclusions, you essentially just, what can you do? You can move the location of eigenvalues, right, of the Dirichlet Laplacian on this inclusion. Then you change your beta. So from applications point of view, you can also enhance the resonance effect by introducing more inclusions, right? Because as I tried to show, the more inclusions you have, the stronger is this resonant and anti-resonant effect. So you indeed can do some tricks. There are limitations, I guess, but you can tweak this beta of lambda in different ways.
Thank you. Anyone else wants to ask or comment on something? If not, let's thank Misha again. Thank you very much, Misha.
Thanks a lot.
Thank you,
Misha, for the talk.